Good morning and welcome to today's webinar, 24 gig SAS, what's new and how to test it. I'm Mike Micheletti and I do product management for Teledyne LeCroy's Protocol Analyzer Group. And we'll get started in a second here. We have a lot of people logging in for this webinar, so that's great. The interest level seems very high on this topic, and there's not a lot of technical information available on 24 gig SAS. I know because I've been searching the interweb for answers myself, and reading the spec is really the only alternative right now, and that's never easy. So this should be good. You'll get a concise summary of the changes in SAS 4. Along the way, I'll try to provide some tips on testing these new features. So if you're interested in SAS 4, I am certain this webinar will provide a large return on investment. Also, I'm really interested in getting your questions, so get familiar with the question box now. Type in any questions you have, anything that's not clear. I'll try to answer as many as I can at the end of the presentation. This material assumes you have some familiarity with SAS in general because we're going to focus on the new stuff, right? Starting with the Gen 5 signaling rate. As I'm sure you're all aware, they use 22.5 gigabaud signaling at the physical layer, combined with more efficient encoding, and that effectively doubles throughput rather than purely doubling the frequency. Really, the biggest changes are down at the link layer with the introduction of packet mode encoding. We'll need to get into the bits and bytes to understand that. SAS 4 does utilize FEC to protect data integrity. FEC checks occur at the subframe level. We'll look at that. Another improvement, APTA or APTA. They basically created a protocol for doing transmitter training on the fly without resetting the link. And then persistent connections. Finally, we'll cover those. They're basically trying to reduce some of the legacy overhead in SAS, probably to try to compete better with NVMe. So a lot of material here. First, a quick market update. It's definitely been a long journey for us SCSI bigots. The SPL 4 spec was approved in September of 2016, so it's taken longer than usual to get to the first 24 gig building blocks. A lot of people will point to the PCI Express 4 and the delays in getting these platforms out. That's been a key factor affecting the rollout of SAS 4 because the 24 gig host controllers are mostly going to be bridging to BY 8 PCIe links. So Gen 4 availability has been a gating item. 2019 looks like a turning point. The industry is now targeting a SAS plugfest for mid-year. And I've actually heard that's now approved by the SCSI Trade Association. So you should be hearing about that soon. I'm also pretty sure you've heard the question, do we really need 24 gig SAS? So just to recap the advantages that SAS enjoys today, as the dominant enterprise storage architecture out there, it can scale to thousands of targets. It has the flexibility to incorporate lower cost SATA devices. It's a proven architecture that can address data center and cloud storage. There's a full ecosystem of software support. And of course, cost per gigabyte. Compared to NVMe, it's very compelling. So as we dig into these new features, you'll see that everything they're doing in SAS 4 is really very consistent with these core strengths that we enjoy today and have always enjoyed with SAS. We're definitely in the true believer camp here at Teledyne LeCroy. We've been involved with SAS test equipment since 2002, and we continue to support the industry. We have two new platforms for 24 gig, the T244. It's our analyzer-only solution with our very latest TAP4 probing technology, and the M244. It's a multi-function platform, also has the 4-port analyzer mode, plus there's a jammer option. And then last summer, we added the Exerciser. And the exerciser plays a pretty important role in these early stages because it can emulate real host and device-side behaviors, so it can be very helpful when testing the initial power-on handshaking for 24 gig SAS. You have very precise control of the logical link layer here, so you can test basic functionality and error recovery, well before third-party devices are even available. Of course, we've been using the exerciser to test our own capture and decoding features on the analyzer side. So using two generators, each running a separate script, we've been able to mimic 24 gig traffic, really testing the tester. So that's helped us stabilize the tools to a level you probably wouldn't normally get at this early stage of 24 gig. It also allows us to create a bunch of trace files that I'll be using to help illustrate the protocol, because now I can emulate all the new features in SAS 4. We don't really have any 24 gig devices that can do this stuff. So we've created some traces, and I think that's definitely easier to learn the protocol compared to reading the spec, right? And one of the things you're going to see is that SAS 4 doesn't make big changes at the upper layers. The vast majority of your SAS 4 traffic will look exactly like SAS 3 traffic at the SCSI layer, very minimal changes to software. Okay, we'll start with some very basic stuff, but it's going to get gnarly quick, so hang in there. I'll go through this section quickly because there's a lot to cover, and as I mentioned, really down at this low layer, at the biggest changes for SAS 4 occur at the logical link layer, or the logical DWORD formatting layer. Sort of in the 12 gig world, packet structures were DWORD aligned, and then in the 24 gig world, protocol traffic is aligned around 4 DWORD frame segments. On the wire, it's not really going to look that different. This is a test unit ready command viewed in our link tracker with the 24 gig traffic on the right. We strip out the FEC strings in this view, but you can roughly make out the SPL structures because of the 2-bit SPL header. And that header is really used to distinguish between segments that contain primitives or data, right? I found they use this term packet mode, and I found that a little confusing at first because it doesn't really correlate to an SSP packet at all. It's really just a chunk of data. It takes multiple SPL packets sent sequentially to make a logical SAS frame. Looking closer at the basic layout of an SPL packet, there's the 2-bit packet header, 128 bits of payload, so 4 DWORDs of data in each segment, and then 20 bits of FEC. Every SPL packet is fixed in length, 150 bits. In the spec, they show the 20-bit FEC pattern at the end, but it's really interlaced on the wire within the payload, always in the same relative position. These are the 3 basic types of SPL frame segments. The 00 and 11 headers are always scrambled idle. The 01, that's the header for primitive segments. Notice that within the primitive segments, there are actually several new primitive types, and we'll cover these. And then 10. That's used to identify logical SSP, SMP, SDP, and idle DWORD segments. So data traffic, it's always going to be 10 as the header. SPL packets are sent sequentially, back to back, in both directions. There's always an SPL packet on the wire, which may just be scrambled idle. Now, it's the responsibility of the PHY on the receiver side to verify FEC and strip out those bits from the packet. It passes the 128-bit pattern up to the link layer, which then reassembles them into your logical SAS traffic. So that's how we yield 128 bits. Again, they could contain primitives or logical SCSI SMP data. Also could be idle. The logical idle packets in SPL are considered deletable at the PHY layer. So what's the point of all this? These packet mode structures are primarily to reduce overhead. AP10B has 20% overhead, now reduced to 17% in SAS 4. This graphic is right out of the spec, and I found this to be pretty helpful in understanding how the different packet types are going to appear on the wire in SAS 4. It defines 6 different SPL packets. I'll start with the easiest to understand, the SPL data frame and primitive segments. Again, your logical SSP frame segment is going to have 10 as the header. And then after stripping out the FEC, you're left with 4 scrambled DWORDs that will be part of a SSP or SMP frame, right? Data frames are always scrambled for EMI. Now, in the analyzer software, we have the frame inspector, which is our lowest level view of the packet mode traffic. It lets you drill down on the raw data for an individual frame. And I'll be highlighting this view a lot because it's the only way to see packets in this SPL format. This image shows segments that contain SSP data, each segment on a separate line. That's the packet header on the left. And we don't show the FEC bits in this view. We're just looking at the 4 DWORDs, 128 bits, always shown unscrambled for data. And so this is basically what makes it up to the link layer. The other SPL packet is the primitive type. Most primitives here have the same role as they did in SAS 3, right? They're used for acknowledgement, flow control, managing connections. But now they can appear bundled together in this SPL primitive segment, usually in groups of 4, but not always. The link layer can send primitive, idle in a single segment. So it's flexible there. Primitives are always sent unscrambled, never mixed with data. You would never see parts of an SSP data payload inside of one of these primitive segments. Another sort of confusing point for me, they elected to encode legacy primitives using 10-bit symbols. Not to be confused with AP10B encoding, just 10-bit patterns. So this table it's actually right out of the spec, table 57. It maps out the character placement for just one of the 4 primitives in a segment. Okay, so still 32 bits to transmit a single primitive, but they don't use the K28.5 symbol as the character now for the first symbol. Instead of your normal comma, they just use 2 bits, which they refer to as the reduced control character. They take the remaining 3 bytes and convert them to 10-bit patterns and place them in the 2nd, 3rd, and 4th position, as you see here. So still 32 bits total. They do this for all 4 primitives in the segment. 4 times 32, 128 bits total. They add the header to make 130 bits. Only then do they do the FEC calculation, which yields 20 bits that are distributed throughout the payload in these other positions. We'll get into that in a second. So still looking at normal primitives, but in our frame inspector this time. This is something you'll really only notice when you go down to the lowest level. When you see 00 in this position, it stands for K28.5. 11 represents K28.3, and that indicates a SATA primitive. So they're representing these control characters with just 2 bits instead of 8 bits. In the frame inspector, we see that there are really 2 important columns. The description on the left gives the decoded primitive name, and then the payload column on the right. That's how we show the raw data for each primitive. So just to clarify, we actually display the primitive parameter select in binary. So when you see 0 in parentheses here, we're showing you binary. Then the next 3 bytes are shown as 10-bit symbols. So the receiver for a packet mode PHY would decode this first primitive here as open accept, because what he sees is the SAS control character K28.5, and then the 10-bit symbols shown here would be recognized as actually at the link layer as 3 of the D16.7s. So that makes an open accept. Okay, now we'll look at the other primitive SPL packets, which are all new as part of SAS 4. This includes binary primitives like the APTA adjust. They now have something called primitive parameters, where you can append additional data to some specific primitives like open, reject, retry. And then extended binary primitives. They function just like any other primitive, only they made them longer. They don't really tell you why, probably because they're used in some critical 24 gig link management roles. But we'll look at each of these in a second. Okay, starting with binary primitives. Again, this is a specific set of primitives, new in SAS 4. I'm showing just a few of them here, but they fall into 2 groups. The deletable, like the APTA adjust. These are just like other deletable primitives. They don't have to go end to end. Their role is point to point. The second type only occur inside a connection, like the new SPL framing ordered set, binary EOF. This is the new frame delimiter for data packets. Binary primitives, well, really all primitives are unscrambled on the wire and can't be intermixed with data. So you'll only see this new end of frame binary primitive at the very end of an SSP data frame. They do a similar trick here with the first symbol, although with binary primitives they use 0, 1 instead of 1, 1. So that identifies that we're receiving not a legacy primitive, but a binary primitive. This is called the control field here, and it doesn't represent a K28.5 as we saw earlier. Instead, it's just a 2-bit identifier for a binary primitive. And those bits become part of the first byte of that primitive. So every binary primitive has to start with 0, 1. This time they're not converting to 10-bit symbols. They just take this 32-bit pattern, combine it with any other primitives they need to send, add the SPL header, the FEC, and send it out. Okay, looking at how the analyzer decodes this in the raw data view. So BEOF3 is a binary primitive, only sent inside a connection. When you look at the payload view on the right, we don't show the control field in binary. Instead, we show the actual hex values because, well, that's how the spec shows it. So that's what we elected to do. Second important point here, for binary EOF, they're using this numbering scheme as a way to define padding for the last segment inside a frame. So not every SSP frame is going to fit perfectly into these SPL segments, right? Sometimes it will. If there's no padding needed, you would use BEOF 0. But in this example, the last chunk of this data frame with the CRC needs 3 padded DWORDs. So the BEOF 3 primitive is used. Basically, this tells the receiver on the far end where to find the CRC string in the previous segment. Moving on to SPL Primitive Parameters. So they wanted a way to send additional data along with a primitive. Here again, it's the first 2 bits that identify if the string is another primitive in the segment or if it contains some kind of parameter data. So this 10B would indicate that the next few bytes are actually some kind of variable data. Below, we have an example as shown in a trace, right, with the closed normal. This is a regular triple primitive, and in this case it's followed by 3 DWORDs of binary data. Okay, the software decodes this a little differently. These here are the primitive parameters, and it shows them in unscrambled hex because that's how the spec shows it. So there's another tab you can click on called the field view, as I'm showing here, and we'll decode the actual parameters. And these are part of the closed normal, right? All related to fairness and setting priority for SMP open transactions. There are only a handful of primitives like this where they want to add this extra data, and those data bits, again, can be up to 3 DWORDs in length. Okay, lastly, extended binary primitives. There are just a few of these. Again, they use this primitive synchronized select field here, which is set to 10. That identifies that it's an extended binary primitive. Okay, these are always 4 DWORDs in length, so only one extended primitive will fit in a segment. And there are only 4 of these defined so far. You know, they might define more, but currently just the 4. The first 3 are considered deletable, so they function similar to an align in SAS 3. They can be discarded going through an expander, and the packet sync, that one has a critical role for initializing the scrambler, as well as synchronization during receiver training. So we'll come back and look at that more carefully. This last one, the end train, essentially it's a marker that indicates the end of the transmitter training pattern. So that would be used during 24 gig transmitter training only. Here's how we show these extended primitives. Okay, again, 128 bits in hex format. So you can see the actual quad DWORD sequence. This is the same way the spec shows extended primitives. In a second, we'll look at 24 gig link training so we can see how these are actually used during power on. And that must be the reason why they extended the length. It's never really explained in the spec why some binary primitives are 32 bits, but these are 128 bits. You know, acoustically, maybe it's easier to detect these longer patterns during link up. If anybody knows, maybe you can send me the answer there. Okay, this kind of summarizes the rules about primitives and primitive sequences, and they're mostly unchanged from SAS 3, right? There are still single, repeated, and continued primitives. You need to receive 1 to be considered a valid primitive. But if you look at the extended primitive, these will be sent in groups of 3 back to back, and you only need to receive 1. So you're building in this additional margin by making these longer and sending 3 in a row. And you only need to receive 1, as I said. Lastly, the rules for triple and redundant primitives are unchanged. Closed normal is considered a triple primitive. Here you still have to receive all 3 to consider this valid. And redundant primitives like break, still sent in groups of 6. And still, here you only need to receive 3. Triple primitives and extended primitives need to span 2 SPL segments. This is something that's easy to overlook in the spec, because we did. This is how the spec shows the sequence. So you're looking at 2 SPL packets here, and notice how triple and extended primitives are supposed to overlap over 2 adjacent segments. And only a line 1 through a line 3 should be used to pad these segments. So those are requirements in the SPL4 spec. This is what it looks like on the wire. A little easier to see here. Closed normal is considered a triple primitive. And notice that it needs to span 2 segments. A line is used for padding as is required by the spec. Okay, just to clarify redundant primitives, there are several tables like this in the spec, and they're helpful for kind of clarifying this point. These are always sent in a sequence of 6, so you'll have to span 2 SPL segments by definition, right? Like we see here with break. Same rules apply as in the legacy versions of SAS. The receiver is supposed to detect redundant primitives after receiving 3 consecutively. No real change here compared to SAS 3. Again, you'll typically see lines used to pad these SPL segments. Final word on primitives. It's also possible to combine different primitive types, including your primitive parameters, your binary primitives, into a single SPL. So there's flexibility there in how you pack these primitives together. Okay, for a complete picture, we should also quickly review a typical SSP frame. This is a write 10. In this column, we decode the field names, like we looked at earlier. Then next to that is the payload, which we show in the raw 128-bit format. Each SPL segment is going to appear on a separate line, so you can see how we decode everything. This is the start of frame. It's a primitive. You can't mix primitives and data, so it's by itself. They'll use a line or idle to fill up the extra space in the SPL for primitives. Then you have your data payload. We're actually separating these as individual DWORDs. Just like with primitives, the data SPL segments won't always fit perfectly in a 128-bit format. So you would send scrambled zeros to pad the last positions in the SPL. Finally, there's binary end of frame. The number 2 here indicates there are 2 padded DWORDs after the CRC. There's a third column in the raw view, which we haven't looked at yet. This is where we show the payload with FEC. So this is actually the only place you can see the actual FEC pattern that we recorded with the analyzer. Okay, so apologies in advance that this is a little confusing because we're mixing binary and hex. Only in this third column we'll show primitive SPL segments in binary, like this BEOF. The 5 characters in parentheses here are the FEC bits. So we're showing them interleaved within the payload, just like they were transmitted. But if you look at the data segments, part of an SSP frame, where you have SSP data DWORDs, they're shown in hex. But here we also show the FEC because we wanted to show it somewhere. So we show the FEC as 5-bit symbols. Primitives, again, are shown in full binary. Data segments are hex plus 5-bit codes. So a little confusing, but let us know what you think. We're trying to make this as useful as we can. Final point here, by default, we don't capture the FEC. So you actually have to enable this. You have to check the capture FEC box in the recording options to actually see these FEC patterns at all. Okay, so we looked at packet mode traffic, all the building blocks of 24 gig SAS. What about link training? What does that look like? Here is the SAS speed negotiation diagram we all know and love. There's not a lot of difference between 12 gig and 24 gig speed negotiation. To get to the higher speeds, all S&Ws still start with RCDT. That's the rate change delay time, the quiescent period where you're supposed to send OOB idle for 500 microseconds. Both PHYs will typically go through S&W1 at 1.5 gig. You would see them transition from a line 0 to a line 1, indicating the point where the PHY has reached DWORD synchronization for that S&W. Moves to SNW2, does the same thing at 3 gig. If either side fails to lock, they would continue with the align 0 for the duration of that SNW time. If it's 12 gig or 24 gig capable, it has to support SNW3 where they do the PHY Capability Exchange. Here again, wait the 500 microseconds. You're supposed to send OOB idle during that RCDT. Then you'll see COM wake from both PHYs if they support SNW3. The PHY capability message itself still uses the same format, SAS3. Obviously, the Gen 5 signaling rate is now defined, but we're still using COM wake signals to transmit PHY caps, and protocol analyzers should, of course, allow you to capture this exchange. The quickest way to view PHY capabilities in a trace is to go to the quick search menu. You just start typing SAS, and you'll see the reset event. It's a SAS PHY reset. If you don't see it, that means it wasn't captured in the trace. But this is what it will look like if you did capture the SNW3. This is the field view. It shows, the fully decoded capability bits. So to get to Gen 5 rate, both sides would need to report Gen 5 capable. If there's any kind of mismatch, they're supposed to pick the next highest commonly supported speed and move to the next stage. Okay, so assuming you successfully complete PHY cap exchange, this is where you may see the devices move to train TX, S&W. Technically, transmitter training is still optional in 24 gig. I'm pretty certain most PHYs will utilize it. And if they do support it, they're supposed to, again, wait the 500 microseconds, then start sending the TX training pattern for 500 milliseconds or until train complete is asserted by the far end. For packet mode devices, the 24 gig training pattern is only slightly different than with 12 gig DWORD mode. They still use the pattern marker to signal the start of a training pattern. It's still 20 UI, then 20 high, and then transitioning to 20 UI low. Each PHY will consider transitions with 38 to 42 to be valid markers. So some built-in slop there. Immediately following the marker, the TTIU structures are sent. Okay, and for the TTIUs themselves, SAS4, is using the same basic approach as they did with SAS3 for 12 gig. No change to the message format, still using DWORD size structures, 32 bits total, separate control word where each side can make coefficient requests. The status word, again, always reflects the status of the PHY that sent it. So 01 would mean the update you requested is complete. So after that TTIU is sent, a SAS4 device is supposed to actually send 59 SPL segments, which contain scrambled idle. So that's 59 128-bit SPL segments, where SAS3 would send just 58 DWORDs of scrambled data. So with 24 gig, the scrambled idle stage is longer, right? They use a new primitive here, ntrain. This is one of the extended binary primitives. So that's used to delineate the end of the pattern and the start of the next. So this basic training pattern repeats while each PHY tries to improve the signal within its channel. Just like with 12 gig TX training, both sides need to signal that they have completed the TX training window by asserting the train complete bit. It would only be considered a valid TX train S&W if both sides get to that train complete step. And then they could move on to the last stage. Now, if either side fails to reach the train complete stage, they're supposed to keep sending the training sequence. If they can't get to train complete within 500 milliseconds, it's considered a failed S&W, and they're supposed to fall back to the next lower speed. and then restart the TX training window. Okay, so assuming devices complete TX training, they move to receiver training. The TX train, the train RX SNW, sorry. This image is from the spec. It shows one direction, but of course the sequence is going on in both directions. And this stage is required for SAS 4. You have to participate in receiver training. Only difference here is that where 12 gig used the train done primitives, in 24 gig they'll now use packet sync and packet sync lost. So these are some of those extended binary primitives we looked at earlier. Both sides start by sending packet sync lost. They're basically using this as a training pattern now. At some point, the PHY gets DWORD synchronization. Then he can switch to sending packet sync. He has to continue sending packet sync until he receives a packet sync from the other side. This actually also resets the scrambler. How does receiver actually perform the DFE stuff? That's all considered vendor proprietary, right? It's not defined in the spec. The only requirement here is that he must send at least 4 packet syncs and then receive at least 1. So send 4, receive 1 before MRTT expires, which is 20 milliseconds, yeah. Okay, so in this illustration, he's sending packet sync, then he finally receives a packet sync. Only here can he be certain that the far end also has DWORD synchronization, right? So he's looking for that. Then the link layer should start sending SPL traffic. If no packet sync is detected within MRTT, that would be a training failure, and they would fall back to the next highest speed. A small side note, this same basic primitive handshake can be used to resynchronize the link in band without doing a full PHY reset. So this is a new behavior. Either side can initiate it, but probably it would first need to detect some kind of receive error or comma detect error. There can't be an active connection open when starting this sequence, but when the PHY receives a packet sync loss now, he needs to basically send the same. And then once 2 consecutive packet sync loss primitives are detected by his receiver with no decode failure, then he can transition to sending packet sync. But again, only after he then also receives a packet sync from the far end would the link then be back up and running. He would reset the scrambler and go back to SPL packet traffic. So anyway, that's how the PHY can now try to relock in band in SAS 4. Okay, just a few more key changes. APTA, or I call it APTA because it's easier. It brings the same basic concept to the TX training, on the fly, in-band transmitter training without resetting the link. The motivation here was to make SAS 4 more adaptive to changing conditions in the storage enclosure. Could be temperature. More likely, bit errors detected at the PHY layer are going to trigger this mode. The spec really doesn't define when you would initiate APTA, so that's vendor proprietary. It does require that all SAS 4 devices support it, so it's a required behavior. Only exception if you have an optical or active cable in place. So you can see the higher layers would need to be involved because they need to basically disable APTA based on the cable topology. This is a trace that highlights a typical APTA sequence. It's different from your power on TX training because obviously it's done in band and it's done with specific binary primitives. Although the mechanics of really what's happening under the hood is very similar to what happens during TX training. This is a simulated trace, obviously, made with our exerciser. So it's not going to really look like this in the wild, but this is really more of the basic sequence. You've got an APTA start followed by an APTA ready handshake. Then the side that wants to improve the eye will request adjustments, and the far end needs to respond when the update is complete. There's a 1 millisecond timer that needs to be observed, before requesting the next adjustment after an update. So under what conditions will a PHY go into this APTA mode? These are the basic rules. The link needs to be in the logical ready state, but no active connection on the PHY. So you have to wait for close. How long do you need to wait? Is there a guard band before you can start sending APTA? None of this is defined. So there's a lot of stuff here that seems to be left to the vendor. In reading this spec, you'll also see that there's no way to actually knack an app to start. What they do is they're going to set some register at a higher layer that disables APTA in real time. And this would happen automatically whenever the PHY has an open connection or is sending OOB or enters low power. So all three of those cases, you're supposed to basically prevent the link from going into APTA based on that link state, right? So you should never really have to knack an APTA command given this rule. Okay, some of the key test challenges for APTA. First and foremost, how do you get devices into this mode? Theoretically, you would, need to degrade the signal on your system somehow. I don't know, maybe put the DUT in a thermal chamber until you start seeing errors. So that's not really practical. So this is where an exerciser could be useful because you have complete control of one side, right? You could create a test script that walks through the APTA sequence, making arbitrary coefficient requests. That way you could at least verify the correct responses. You may also want to verify that devices don't respond to APTA requests, like during a data transfer. Here it would be probably easier to use the jammer. You could wait for one side to open a connection, then replace the open accept with an APTA start. A real device should ignore this and reply with break, even though the connection isn't established yet. The management layer should disable APTA as soon as he sends that open. So that's the behavior you're looking for. This is probably a good time to do for a 2-minute chalk talk on the differences between our T244 and M244 test platforms, because TX training, APTA, this is going to be a critical part of your interop testing. And our T244 is really designed for this role. This is the platform that has the TAP4 probe, which is really a 4th generation linear amplifier front end. It's designed to pass the native 24 gig signal through with minimal distortion. This means you'll see amplitudes that are flat from the input connector to the output connector on the analyzer. With the M244, which supports the jammer, the signal path goes through the FPGA. So by definition, it's a redriver, and it's going to affect link training. With the M244, when you actually first power up the link, each side is actually link training with the tester. The SerDes on the jammer is the link partner. It behaves just like a valid 24 gig SAS PHY, only after it detects that, both cables are connected, is it going to actually start the link bring-up sequence. It goes through all the speed negotiation windows like a real device. It'll interpret and respond to any TTIU requests. It goes through receiver training directly with each side. Once we get to DWORD synchronization, we pass everything directly through to the far end. We're still regenerating every symbol, right? But it's an exact copy of all this traffic from that point on. So everything from the identify on goes end to end. And the system always runs in this jammer mode. So it's basically spoofing the devices during the initial link up and then seamlessly switching to a pass-through mode. The analyzer records everything from the devices, that you're testing. So you would see all the messages shown from the green arrows here, but it actually swallows the S&W traffic from the jammer PHY. So you'll see the TTIU change requests, coming from the DUT, but they, won't necessarily correlate with the other side because they actually don't get to the far end, right? So that's a real important distinction. With the T244, the probe is virtually invisible. No redriver, no added latency. So this is where you're going to want to debug any link training issues. Same for the APTA features in SAS 4. You'll avoid any distortion by using the T244 for this testing. Use the M244 for functional testing for error injection at the protocol layer. If you're doing ASICs, backplane, any kind of storage subsystem, you're basically going to want both of these in your lab. Okay, FEC, that's new in SAS 4. Initially, the PHY group thought they might be able to get away without FEC for 24 gig links. In the end, it was decided they couldn't get to the 10 to the minus 15 on the bit error rate without it. So they add 20 bits of FEC to every SPL segment, which can correct up to 2 bad symbols anywhere in the packet. So this provides added margin for loss in the channel. The FEC calculation starts with the 130-bit SPL packet and payload. This is after scrambling, in the case of SSP frames. This is used to generate the 4 5-bit parity symbols. These FEC bits are not scrambled, never scrambled, but they're interleaved across the SPL segment. And that is supposed to provide better protection for burst errors. RSFEC calculations are pretty complicated, so it's really beyond the scope of this presentation. I'll just touch on the test implications. So how do we test FEC? The easiest way is to use the jammer, which can randomly add FEC errors to live traffic. You could also do these kind of bit flip errors with the exerciser, but the jammer, much easier. It lets you select the events from a pull-down menu. You could pick an SSP frame or any primitive, really, like the entrain. You would then select which type of error, as shown here, and you have the ability to insert correctable or uncorrectable errors. By using the jammer, you could basically see how the target handles the error and then any recovery that may happen at the system level. How does the analyzer actually handle these correctable FEC errors? The key thing here is the analyzer is capturing the bit stream, errors and all. So if there's a bit flip, the analyzer is going to perform the same correction that a PHY would, right? You won't actually see anything in the trace. We don't flag correctable FEC errors. Now, if there's an uncorrectable error, the PHY would first try to correct the error, right, by identifying the location. If it determines that there are more than 2 symbols with errors, it would give up and send a decode failure message to the PHY. That SPL segment would be discarded. The analyzer is still going to record it, or try to record it. What happens next really depends on the type of traffic. An SSP packet would probably be shown as unknown with a CRC error, like you see here. If you have a primitive segment with an unrecoverable error, that would be trickier. Probably some kind of timeout or retry condition would be visible. Okay, just a couple more slides here. Persistent connections. They were actually introduced back in SPL 3, but they're getting more attention now. It's a specific feature for direct attached server storage. where you may be utilizing SAS in more of a point-to-point configuration. The idea is that you can reduce latency by just leaving the connection open. Really, it's a direct response to NVMe storage, which is connectionless. So now you can set up a persistent connection, especially for flash-based storage. Hyper-converged infrastructure is another place you might see persistent connections used. And this feature does require support on both the initiator and the target side. It's optional, but if it's supported, it'll be reported in the identify string. Once an extend connection is enabled, both sides start a 100 microsecond timer, and that resets every time it detects an EOF delimiter. Now, they're not receiving or transmitting data frames. They would start sending an extend connection primitive on the expiration of that 100 microsecond timer. So the extend connection primitive becomes a keep alive, and the connection basically stays open as long as the PHY is receiving a valid frame or another extend connection primitive. How do you close a persistent connection? Either side can be directed by a higher layer to send the done normal. So normal close procedure here. There's also a 1 millisecond deadman timer, and that's running continuously. It also resets with every SSP frame or extend primitive. If 1 millisecond goes by without seeing either event, this would also cause one side or the other to close the connection. So that's another important timer that you probably want to test. And so assuming that you have devices that support this, you'd want to test both of those timers. You could start by waiting for 100 extend connection primitives. Make sure the link is in this mode. Then you could remove the next 10 in one direction to kind of force the 1 millisecond timeout. You might have to play with the timing there a little, but you would want to see a done close within 1 millisecond of that last extend primitive. Another area, flow control testing, should also be part of the plan, because you could go hours or even days without a close. So a credit starve test might start by making sure you're in an extended connection mode, then doing multiple small block IOs. After some interval, start dropping every other already from the initiator. The target should eventually issue a done credit timeout. Timing here would kind of depend on the devices, but do your devices manage that credit buffer correctly over long time frames? There's a lot of corner cases to cover here. Okay, so that was fast and furious. I hope you stuck with us. And we did look at most of the new features of 24 gig SAS. Of course, you still need to test all the legacy stuff at 24 gig, so it's a lot of work here. Teledyne has a division called Austin Labs that offers test services, and for your information, they're already developing test scripts specifically for SAS 4. They also have experience using Python and doing automation for a range of different tests. So, if you need help, talk to Austin Labs. They might be able to get you jump-started with your testing, at least with some of the corner cases. Okay, special thanks to our sponsors, the Sierra T244 and M244, that made all these traces possible. Again, if you missed any details during the presentation, there'll be an on-demand playback version of this webinar posted in the next few days. And let's go to questions. So this is always tricky to get this interface to show up the way I want. Okay. Let's see, someone asked, are link rate management primitives used for rate matching? And the link rate management, that's one of the new binary extended. I don't think there is any change in rate matching. I have seen PHYs that primarily use aligns or scrambled idle segments for rate matching. So the link rate management primitive, as far as I know, is for clock compensation. And so similar role, but I think that you're going to continue to see aligns for rate matching. Okay, what else do we have here? Someone asks about the slides. Of course, I will make the slides available. I will send them out right after the presentation. Can the analyzer trigger on a correctable FEC error? And we do have an FEC trigger, but it only detects uncorrectable errors. So currently the answer there would be no. If triggering on correctable errors is important, let us know, because that is something we possibly could add. How are binary end-of-frame primitives handled when transmitted to a legacy 12 gig device through an expander? Okay, so binary, so it's a 24 gig upstream, 12 gig downstream. So it would convert it. So none of the new packet mode primitives would be recognized by a PHY operating in 12 gig mode. So it would need to convert the binary end-of-frame primitive to a normal end-of-frame primitive. And so that is something, obviously, you'll need to check on both sides. Okay. I don't see any other questions. Okay, so anyway, that is great. Appreciate the questions. And if you do have any other, by all means, send them to my email. I'd love to hear any questions, and we'll certainly respond. And if you want access to our trace viewer software for SAS 24 gig, drop me a note, and I will send you the password and some of these sample traces we used. And with that, we're right at the top of the hour. We'll wind up our presentation and look forward to another 24 gig SAS seminar coming to the same venue in the next couple of months. Thank you very much.